Hello, my name is Matt Harris. I'm a solutions engineer with M2 Technologies, and welcome to the webinar on Alias and Inventor Interoperability. For more information and more webinars, please check out our website at www.m2t.com. Design drives success. Now, when we take a look at industrial design in the product development cycle, it's important to realize that the design of a product really is that product's lifeblood. It's its identity, it's how it's perceived to the outside world. So obviously the design phase of product development is very important, and we need to really make sure that we do a quality job when it comes to the design of our products. Some of the challenges that we face as designers is really first finding a process that works. It's every now and then we get lucky and we come up with the right concept the first time. We pass it over to engineering. There aren't any mistakes. It never gets passed back to us. They model everything up and get it ready for manufacturing exactly how we want, and they get it to market on time and under budget. And actually that doesn't happen too often. So every once in a while, actually it's never happened to me, but I'm sure somebody out there has been able to pull it off. Since that's not the norm, it's really important that we develop a process that makes sense, that's easy for both the designers and the engineers, and it allows them to both have the freedom to do their jobs. So it's important to understand not only the strengths and the weaknesses of both the design department and the engineering department, but to have a clear process of what happens to the data as we go between those two disciplines. And I'm not just talking about one way, we need to look at both ways. Part of that is, and really paying attention to that data exchange, is making sure that our original design intent is carried through the entire process. And there's a lot of talk out in the industry about this, is leverage as much of that digital data as possible. And really the combination between the Alias product and the Inventor product is the most foolproof way to keep that together. And I'll be showing you some examples of that. Design decision delays, really that's being able to figure out the accuracy and where the design is going as early as possible. And that also goes back to that data exchange. Being able to work over real product internals, real product constraints, and then not making guesses, because the longer we wait to make decisions, the more expensive it becomes. And that's especially true when you start getting into prototypes, and you want to be able to make just as few prototypes as possible. They're important because you need to really understand what that product looks and feels like, but obviously the more that you create is the more time, and hence the more money. And then it goes back, it's all about that collaboration. So really the top three keys here are all about the collaboration between the design and engineering. The product on the design side is Alias, and in this case Alias Design 2010. Alias really is the only industrial design tool out there that is capable of allowing designers to work with high-end sketching tools and then go directly into Class A technical production services. So it's the only tool that covers the entire industrial design process in one package, and that's pretty incredible. There's a lot of surfacing tools out there that really aren't made for that industrial design cycle. They're just surfacing tools, or you might have great sketching tools, but then where do you go from there? So Alias is the only package that really combines everything into one single product. Some of the key capabilities of Alias is obviously creating as many concepts as possible, and this goes back to we want to do a lot of designs in as least amount of time as possible because we want to be efficient, and we want to make those decisions early on in the process. So the more accurate and the more realistic that our concepts are in the first place, the more likely we're going to make a correct decision early on. And we also have great interactive tools such as bookmarks and visualization tools, real-time visualization tools, the ability to mark up and sketch out new ideas directly on top of that 3D data. So here you can see examples of sketching over top of actual 3D data, developing new concepts, new ideas. Maybe it's graphic and logo work, what have you. And then really that last stage, how do we get that information that we've developed inside Alias, how do we get that over to the engineering side of things? And then on the flip side of that, how do we bring that engineering data into the Alias side so that as we're developing our sketches and our surfaces, we're developing those that are realistic and viable as well. It's all about being viable. Yeah, we can design all we want, but if it's not able to be produced, we have some issues. So the typical, and this is really watered down and sterile, obviously it's a lot more complicated than this, and there's a lot more factors, but when it comes to CAD, this is the basic workflow that most designers work with. I'm not saying this is the right one or what have you, but it's the basic generic workflow of how we work. What I'm mostly concerned with today is what happens after this refinement stage. So we get everything down to these final models. It's ready to go into production. It's going into engineering. What happens from there? What if there are changes? How do we handle those types of scenarios? As far as data exchange with Inventor, the types of files that Alias can read and write that are interchangeable with Inventor is actually the DWG file. You wouldn't think that would be the case, but it actually is. And this is kind of the stopgap before Alias and Inventor could read each other's native files. Now that that exists, more likely you're going to be using the open and import commands in both software packages and just opening the native files from each other. Here's a great quote that I picked up, and it really highlights the fact that there are tools out there that are cheaper and people swear they can get their job done with, but in reality it's not really worth it. The amount of money that you're saving, you're either losing that feel by using a solid parametric modeler for design, you're losing that organic, that hand feel or that character, or you just don't have the ability to get things done quickly. So you really need a package like Inventor if you want to be doing some world-class design these days, or Alias. Autodesk, as you know, of course, acquired Alias, and they're committed to the industrial design community. They're now some of the main sponsors in a lot of the community events, and I'm really excited to kind of see where Autodesk will be going in the future. Alias and Inventor are actually, pretty mature products at this point, and I know there's a lot in the works, and I'm really excited to see where this goes. First thing we're going to take a look at is the transition from Inventor to Alias. So here we have an Inventor assembly, and if you take a look at the browser over here, we have some subassemblies and then some parts on those subassemblies. So this is what it looks like inside of Inventor before we open up the assembly file inside of Alias. So this is typically what engineering would kick out, maybe some product internals. It could also be some 3D ergonomic data. So we'll take a look at what that looks like inside of Alias. So in Alias, we'll just use our file open command, and I will browse to that same assembly. There are all the parts. Here are the assemblies, and I'm going to choose the same name, the controller_demo.iam, and open that up inside of Alias. I'll accept the settings on the model coming in so that I know that if I model anything from here on out and it goes back into Inventor, that the tolerances and the fits are all going to match up. Here is the model inside of Alias. I'm going to go ahead and quick shade this so we can take a look at the color information. So you'll see here that it looks exactly like it did inside of our Inventor session. This is great because now as we start to sketch and develop ideas, we're working over top of actual physical proportions and size. One caveat when bringing in Inventor data is it's one grouped object. So if I pick any of these components here, the entire assembly gets selected all at once. There is a way to select individual components and move them around, and the easiest way is to use your object lister. So if you go to Windows, Object Lister, it'll expand and then show you everything that's on, in this case, the default layer. So here is my top level assembly, and as I choose through here I can pick individual components, so you can see it's highlighting both the batteries, or I can select sub-assemblies or dig down in and select items on those sub-assemblies. Then from there you might want to choose, say, the batteries by holding down the shift keys, throw in a move command, and then move maybe the position. So if you want to try different configurations of the engineering data, you do have the freedom to do that as well. I do recommend going ahead and creating layers and organizing it on layers as well. For instance, if I call this circuit board, and then we select the circuit board and assign it to that layer, that will also nicely segregate your data and then also give you the ability to quickly pick it just by using the pick object command from the layer dropdown. You could also then quickly turn off the visibility and back on as you're working. Typically at this stage, the next thing a designer would do is start to develop their concepts, whether it be 2D or 3D. So to show that, we would typically start a new canvas, and then I'll take a look at my top view here, and then move that canvas into place. You might also want to raise the canvas up so that as we're sketching, it's on top of our data. So at this point, it's just a matter of grabbing our paintbrush, our pencil tool, and I'm sketching with a mouse, so don't judge my sketching right now. And then go ahead and sketch in your lines. Now, just to show you really how this works and where we go from here, I'll open up a more developed file. So as you can see here, the designer's begun to develop a rough sketch just based on where the location of the components are relative to the sketch. And then from there, the designer can take it to the next level and begin to really do some nice finished sketches to develop the form. And then from there, it's just a matter of developing the surfaces. So if we jump over back to our 3D environment here, and we can turn on the original primary slab surfaces, you can see where the designer was going with this model. From there, the designer went ahead and developed some final surfaces. Right here. And at this point, it might be a good time, because we have a nice closed solid, to send it off to the engineering department for them to start develop the internals. So we'll just grab these surfaces here. Now I could just do a save, but just to grab only the surfaces that I want, I'm going to export these out to my desktop as a native wire file. Oops, it helps if I use export instead of import. There we go. So we'll throw this on our desktop, and we'll call this controller for Inventor. Then bouncing over to our Inventor session, we'll put on our engineer hat right now, and we'll use the open command, and we're just going to open that native wire file right off the desktop. So I'm going to sort my files of type to alias native wire files, pick my surface file, and hit the open button. I'll then get my derived alias dialog box here, and if I imported more than one layer, it would show up segregated here so that I can turn different layers on and off. I only had one layer with surfaces on it, so I'll keep that entire layer. And there are the surfaces inside of Inventor. Since this is a closed solid, once a closed bunch of surfaces inside Inventor are stitched, they do become a solid. So I'll go ahead and use the stitch command, choose my surfaces, and just leave the default tolerance. And it did pick up that everything was closed and created hence a solid for us. I'll then go ahead and shell this out to make it a hollow part, and then I might realize, hey, I needed to find a parting line for this, and I might want to go back and do that inside of Alias. So I did do that. I had another file that I had made that contained the original surfaces that we just saved out to Inventor, and then also I created a surface that intersected those surfaces to define what the parting line is going to be. instead of just exporting out just that parting line surface, we're just going to go ahead and save this file on our desktop as well. So we'll call this game controller part line. Then by going back into Inventor, to bring in those surfaces, instead of using the file open command, I'm just going to use the import. If I go to my Manage tab and then use the import function, I can browse to my game controller part line wire file, open that up, and we'll get that same derived alias dialog box. Now, like I said, the main surfaces were on this layer and my parting line surfaces were on the other. Well, I already have my main surfaces from the other wire file, so I'm just going to click this to not include those surfaces and only bring in the parting line surface, because that's the only data that we need. There is our imported parting line surface. If you look over here in the browser, you can see it there as well. And then using that surface, I can go ahead and I'll use my sculpt command, and we'll sculpt out and get rid of the top section, and we'll work on the bottom section first. So there we have a nice shelled out bottom portion of our game controller, and now it might be time for engineering to start working their magic and making this manufacturable. So from here, we'd probably define a work plane at some angle, and I'm going to choose 10 degrees. That looks about right. And then I'm going to offset another work plane up to a certain amount, because we're going to define some bosses. We'll turn off the visibility of both the planes, and we'll start a sketch on the second one. I then need to place in some work points for my bosses. So I'll place one, say, here and here. And then we'll use the plastic part tool for boss. Put those into our model. And then we'll add some fillets. Now I did want those to be on both sides, so actually I'm going to move my end apart up and do a mirror. Mirror those over, and then we'll add a couple more fillets. Okay, so there we have a pretty good jump on our model already. So we'll save this to the desktop as our Inventor part, which references our other two alias files. So that's basically going from Inventor with the internals to Alias, and then developing a concept in Alias wire files, bringing those back to Inventor, and then creating our engineering portions on those actual surfaces. The whole point of this is knowing the strengths and weaknesses of both software packages, and knowing what the line is between you, the designer, and the others, the engineers. Because there's certain things that they also have their own strengths and weaknesses, just like we have our strengths and weaknesses. So this allows a very good repeatable process to use over and over again that is great. I mean, now the real question comes in, what happens if there's a change? So I just want to show how Inventor and Alias handle changes down the road, because the further down the road that we go in product development, the more expensive the changes become. So for this case, I'm going to open up another data set, and we'll come back to the game controller in a little bit. So I'm going to bring up the helmet data set. So you can see here we have a helmet, and this was all created inside of Alias. It's just a shell. And this was great. Let's say this went into engineering. Actually, let's go ahead and do that. So I'll grab the surfaces here, and we're just going to save these out. Actually, you know what? Let's just save it. So do a save as helmet on our desktop, and we'll bring the data inside of Inventor. There are surfaces. This time, since I don't have a closed shape, when I stitch it, it's going to remain surfaces. But the difference is that once they're stitched in Inventor, we can treat it as if it's a solid. Real quick, I'm going to scroll through and make sure there aren't any gaps between any of my surfaces, depending on my tolerance, and we look good. So then I'm going to go ahead and apply some fillets. So let's make that just a little bit bigger. And then instead of using the sculpt command to make it a solid, this time I'm going to use the thicken offset command. And instead of thickening faces, we're going to do the entire quilt. We're also going to make sure that it's offset towards the inside, and we'll give it a thickness. We'll then hide the visibility of the original stitch surface, and we'll mirror the helmet over. So once again, we've made the surfaces that count and that are important to us as designers in Alias, kicked those over to Inventor, and then made it a developable solid that we can then make manufacturable. I'm going to save this on the desktop. We're going to call this just helmet IPT. Now we're going to take a look at what happens if there's a change. So when I go back to Alias, you'll see that I had some more layers here, and these vents were created from these curves. So if we look at a top-down view, you'll see that those line up. And if we adjust those curves, the vents change. And let's say we had a design change come down, and we want to take a look and see what the helmet would look like if it had a different vent shape. So if I come in here and change the position of the curves that got projected on those surfaces will update. So this is just part of the basic core functionality of Alias. So what we're doing is we're making a pretty drastic change to how this model looks, but you'll notice that we're not adding or deleting any surfaces. And because we're not, Inventor does update really nicely, at least in theory, so we'll definitely test that out. So these surface names are exactly the same, they've just modified, they're changed. They're not any new surfaces and there's not any deleted surfaces. So my next step is I'm going to go ahead and save this, and we'll make sure that inside of our Inventor file that it updates. So I'm going to grab my Inventor helmet part, hit the open button, and we'll see over in the browser that there's been an update. Now it's not going to update until we tell it to say, okay, go ahead and take a look and make a comparison to that original wire file, and it's only going to update when we tell it to. What you need to do to update is you hit the update button at the top. It's then going to go back, it's going to look at that wire file, swap it out, and then repair itself and fix itself down the browser tree. So if everything works properly, these vents will update. You can see there that everything came through, swapped out, and recomputed itself automatically down the line. And the reason it did that is, remember I said these surfaces all were maintained. So it knew, for instance, the intersection between these two surfaces had a fillet in it, and that's why the fillet was able to be picked up and computed. Next thing we're going to take a look at is something a little more complicated, just to show the power of this interoperability and what to do if we swap out surfaces and we don't have as clean as an update. So I'm going to open another file, another housing. So here we have some features that were performed on an alias model, and you can see there are a lot of them. The engineer has been doing a lot of work, adding a place for a display and a cord. If you look inside, you'll see that there's been a lot of internal ribs already started to be created, battery covers, all kinds of things. So there's been a lot of work to this, and any changes could really have a drastic effect on how much time it would take for the engineer to remodel all of this information. Now, if you take a look at this display area, there was a change that required this recess to be pushed forward and the display itself to be pushed forward by 300 thousandths. So in essence, we need to get rid of this surface, and since this split was already in here, is add a patch, a new surface through here. So in Alias, we'll go ahead and make that change. And I'll show you the original file that we started with, and then the final file that is then going to be able to update this. So we'll open up. Here is the original file. And you'll see here, this is the area that we need to increase. So then the resultant file was this guy right here. So you can see we've added more distance there. We've had to delete and remake just these top surfaces here. Now I need to get rid of this guy, the original one here, and then we have our surfaces now with which we can work with. So we're going to save these out over top of what the alias file was that the Inventor file was referencing. Now when we go open the Inventor file, we should be cued that there's been an update, and there has. So we'll hit our update button, and this update isn't going to be quite as clean. We're just going to hit the accept button, and you'll see the bottom portion of the update came out fine, and that makes sense because we didn't affect any of those surfaces. So Inventor knew what surface was which surface during the update. What it doesn't know is what to do with those new surfaces that are at the top, and that's why a lot of these features have failed. There is a way to fix that and to reassociate which surface is which surface. And the way we do that is just by right-clicking the original alias surfaces, and we use the Update Associations option. This will then display the original surface here and the new surface. And we just need to tell it that those two surfaces are going to be the same surfaces. So if we pick the new one and the old one, we can either delete them or we can say and match them up. And now those are matched up. We can also sort by layer. So if we want to take a look at the F recess layer, we can also see that we also need to match up these surfaces. So we see that this surface is going to be matched up with that one, and this surface is going to be matched up with that one. Once we've set everything equal, Inventor will then fill in the blanks and update all of the names so that all of our features will be able to recompute themselves. And there we go. The surfaces have been moved up for us, which will give room to be able to move the display, and you'll see that everything is computed through. Now, one other thing I want to mention is when the engineer originally kicked out the internals to the design department to be able to design the housing around this, he had it on a different coordinate system than what the designers preferred. So the internals came in, and the designers in their freeform environment inside of Alias rotated along the origin at 90 degrees so that they could sketch from a top view, and it just made it a lot easier for them. The problem with that is when the surfaces were brought in, they were actually brought in at a 90-degree angle. Well, one of the nice new features of Inventor 2010 is the ability to work with solid bodies and move those bodies in 3D space and have those be remembered. So as that surfaces came back in, the very first command that the engineer used was the move body command and rotated it 90 degrees down around the origin into place. That way the designer can continue to work in their coordinate system and the engineer can continue to work in their coordinate system and not have any issues. So that was a really complex update that was done very quickly and would save us a ton of time in the industry. And now Alias and Inventor are the only two design and parametric solid modeling packages that have that capability to allow both their designers and the engineers to work in their preferred environment. I also want to show maybe what happens when that update association doesn't go as cleanly as we would like. So I'm going to open up the game controller file that we were working with originally. And I'm going to make a global change inside of Alias and see how that update affects us in the Inventor environment. So let's open that game controller. We'll use our lattice rig and we're going to make a global change to these surfaces. So going to my object edit, my rigs, here's my lattice rig, and I'll select the surfaces I want to affect, accept it, and we're going to add a split. So we'll add a split, say, around there, accept the split, and then we're going to go ahead and pick the corners we want to modify. We want to scale them, and then we're going to engage the model. We'll kick in the sides a little bit. You can see there we end up with more of a kind of a Batman symbol looking controller, and we'll go ahead and accept those changes. So I'm just going to do a simple save because we've modified those surfaces. Now when we use this lattice rig tool, it essentially recreates all of these surfaces from scratch to be able to be clean. That's great for Alias, but on the Inventor side, that means that it just lost track of all the surfaces inside of Inventor. So we'll take a look at how we can go about fixing that. So we'll open up our original controller. You'll see that it picks up there has been an update to the wire file, and that we need to fix that. So we'll hit update. And this time there was an issue. Notice we don't see the new shape at all, and we do get a warning that there was an issue with this wire file. So a simple right click and update associations, we can see we have a bunch of issues. Now if you had to, you could one by one match up all of these surfaces and have it repair itself, but obviously that would just take a ton of work, and we really don't have that kind of time. There are other ways that we can deal with this. What we can do is, since the engineer used work planes and work points and extrude twos and not necessarily projecting any geometry from this original wire file, that we can just simply swap it out. And that's something that's very important, is as you're working with your engineers, make sure that they understand that the more they reference the wire file itself when they're building the rest of the model, the more likely it is that it's going to fail. So you don't want to use project geometry as much. You don't want to start sketches on faces of wire files. Use your work geometry, which is a lot more powerful and flexible anyways. So to swap this out, we're going to move our end apart up. We're then going to delete it, and we no longer have our wire file in there. And then this time we're going to import that same wire file and basically start over from scratch. There are surfaces. They're updated. They have the new look. Bring those in, and now we do know that this next stitch surface is going to fail because it isn't going to be able to recognize the surfaces. So let's fix that first. We'll go ahead and accept it. We'll right click it, we'll edit it, and we'll just simply reselect the surfaces and restitch them back together. And since we were smart and computed most of the rest of these using as little reference as possible back to the original wire file, when we drag this end apart down, we'll have less fails. If there are any, just go ahead and hit accept, and everything came through just fine except for those fillets. And to be completely honest, that's what I would expect to fail, because these fillets were placed on actual edges between surfaces. So you just have to come back in here, pick those, and then if there are of course more features down the road, you always want to start at the top, fix from the top, and let it filter down, because other features rely on the original features. So you always, when you fix a model, want to start at the top, and things start to then fix themselves down the feature tree. Okay, so in summary, if we take a look at the design challenges that are brought up in the intro, and we take a look at whether or not we address that or not. First one is a repeatable process of innovation. Do we have something that we can repeat and over again and be successful? And we can. And really the key to all of that is know each application's strengths and weaknesses. Know what an Alias does well, know what Inventor does well, and then draw your line accordingly. And then maybe you even document the process so that you can train others and make sure that both the engineering department and the design department are trained and know how to handle those exchanges. And it'll go a long way in saving money and time. As far as design intent, really there's no better way to maintain your intent than to actually provide the models that are being manufactured. So if the details are important to you, then you model them. It's pretty straightforward. As far as decision delays, there's really no way to be more realistic and more accurate in the data that you're passing back and forth than to use that actual data. So by far, the workflows that I showed are going to go way above and beyond probably what you're doing today when it comes to making decisions. And then as far as the collaboration between design and engineering, I think it's pretty obvious that this is the solution. When it comes to best practices, there are some things you need to keep in mind, and this goes back to knowing the strengths and the weaknesses of each of the packages. On the Alias side, make sure you keep a backup set of your major surfaces. So even most people do this anyways, so that if you need to make edits, it's easy to swap out big primary surfaces and redo some of the details than to have to remodel everything from scratch because you've deleted some of your surfaces or your curves that created those surfaces. Really the best way to go about that is use data management. If you're in an environment that already uses Inventor, chances are you have a data management product like Vault that you can vault your data, and that way you don't have to worry about keeping backups because you can always get a previous version. And then only model the surfaces that you need that alias control over. If you have a simple G1 fillet, just a tangential fillet, do it in Inventor. Why do you have to do that in Alias? I understand if you need to do some visualization to show the product and what it would look like early on, but you don't have to worry about those levels of surfacing in the final production. Maybe in the transportation automotive industry that might be a little bit different, but if you're just doing products, that's more than fine. And then also organize your data by layer before you export or save, because Inventor does keep track of what layer the surfaces are on, so you want to keep that nice and organized. And then on the Inventor side, take advantage of the multi-body solid movements to maintain those coordinate systems. So make sure that you're taking advantage of that. And then, like I said, avoid projecting geometry from the other models. So from the alias models, you don't want to bring those in and use projections, because if we swap or need to update those, they'll fail. And then always use work geometry instead of faces to create sketches on. And that's just general good practices in general anyways with Inventor. And then, of course, using commands such as to next as opposed to and selecting a surface will go a long way. And then if you do have a model that blows up or you run into a bad situation, always repair from the top and let it filter down. So the features that are below always reference features that are above. So then you always want to start at the root of the problem and let it filter down. So that's all I have, and hopefully you got something out of this. And good luck. And if you have any questions, feel free to email me at mharris, mharris at m2t.com, and I'd be happy to help you out. So good luck.